Good afternoon, good morning, or good evening, as our speaker of today is, given that he is 6 hours, has 6 hours time difference, he's ahead of us. Great pleasure to introduce Dr. Konrad Stopczak. My name is Bert Hoffman, I'm the chair of epidemiology, and it's a great pleasure to welcome you at this seminar in the series of the Department of Epidemiology of the Harvard Chan School. Dr. Konrad Stopczak is the chair and the professor in the Department of Epidemiologic Methods and Etiologic Research in the Leibniz Institute for Prevention Research and Epidemiology, which is one of the major institutes of this nature in Germany, in Bremen, Germany. He focuses on methodologic issues, as you will discuss in this seminar, and also in terms of application. He is a molecular and cancer epidemiologist. Dr. Stopczak, Konrad, it's wonderful to have you, and I would invite you to take the floor and discuss epidemiologic methods and data science, stronger together, without even a question mark, I understand. Yeah.
Without a question mark. Thank you so much, Bert, for this very kind introduction and for inviting me. And thank you, everyone, for joining. I would like to discuss these two things together with you and without a question mark behind them. And yes, we have data science, and maybe that is just an iteration of things that we have previously known under different names. I put on a tie today to make sure that you don't mistake me for an informaticist. I don't actually know anything about data science, I might say. So that's why I'm defining something new, and that's epidemiologic data science, which simply means caring for our data before we put it into a model or into a paper. And I'm, of course, not the first one to care about this. This is Ken Rothman giving the Cotter lecture about the time when I was a student, and he coined this rift between epidemiologists and their data, essentially that we were putting lots of ratio measures into our papers, but we're afraid of showing the descriptive data, the count data, the actual data. And I would think that data science approaches will actually help us with that. So in some ways, though, we're getting a little bit ahead of ourselves. We come from an age of calculators, pretty fancy calculators and spreadsheets, and we're now trying to move to a world of artificial intelligence that does our epidemiologic analyses for us. And in fact, the big players of those classic analyses have long recognized, well before the advent of large language models, that this is where the future lies, and have heavily invested. The point that I'll try to make today isn't necessarily about these logos that I put here in the middle, but it's about not skipping an important step in between, and that's a step of algorithms and of structure in our data. What do I mean by that? Let's look at a typical workflow in epidemiologic analyses. And might start with a PI submitting a grant proposal, then emailing a study team to collect the data, those data getting stored somewhere, then email conversations with the trainee about an analytical project, results being sent back, results being put into a progress report to a funding agency, and then, of course, the next trainee, and things start over. And to me, this, of course, artificial example here raises a few questions. When this PI submits a grant proposal, what do the PI's colleagues know about those plans? But those emails that are being exchanged, where are those? Can someone learn from them? Can they help us reconstruct how the study was done? Who stored what data where, and when? Again, were those emails? And then the results that are in those emails, what code made those results? And the results that made it into the progress report, again, based on what data, what code did those results came about? And that poor next trainee, how's that person gonna reconstruct that entire email trail? So I'd love to start off with something that has my name here on, but is not at all my idea, and is something that the chronic disease epidemiology research communities at Harvard, so the Nurses' Health Studies and the Health Professionals Follow-Up Study, have been practicing for decades, and it's really putting people first, and people besides the core research team. It's other investigators, researchers from other teams talking about hypotheses, analyses, plans before analyses start, building teams, and then coming back together to discuss results among peers with methodological and subject matter expertise on these very same cohort studies before things are published. Then a critical part, all the analytical code and its log files are archived centrally, and the code is reviewed by a programmer. And then lastly, those results that made it into the manuscript, actually checking them against those logs to make sure that they were the same. And then there's process adherence. Let's first focus in a little bit on the data science part that is in addition to this long established process, and that I believe could enhance this process and can enhance perhaps a lot of other processes. So how do our analyses produce results? We may write code in a text editor, and I tried to dig out SAS code that I had written as the analyst a few years ago here. We submit that code to a server that houses the data. We receive a log file with the results, already a PDF, but a lot of things that we don't want to know, an extraneous level of precision that we're not going to report in our manuscripts. And then we manually type those things into Word and on the fly round those results, perhaps. So why is that process so laborious and error-prone? Well, it's unclear which data were read in. We look at this report here, it's not going to tell us. It's unclear which data were read in and which code produced which result. It's unclear what motivated each analytical decision. And the numbers are manually being transcribed. We know about the error rates of those processes. And this is perhaps the biggest thing. Even the tiniest change to the analysis is so much work to redo. There's always that one participant who doesn't actually fit the inclusion criteria, and that you may need to exclude at some step, or the one tiny change up front in your exposure definition that you realize later on. And that means you have to rerun everything, you have to compare every number that comes out of those logs against what you've already typed into your draft manuscript and see if something has changed. As someone who's trying to supervise people on doing those things, I'm not going to ask people more than twice if I know it's more, that it's so such a hassle to change even the tiniest thing. So this is a big impediment, I believe, to doing better analyses, to doing sensitivity analyses, to just thinking more about the alternative approaches we could take. And then good luck with emailing your code and all the output that it produced to help have someone look at line 563 to line 597 to perhaps find the error that is occurring somewhere there. So these things are really hard, but they can, in 2025, we now do have the tools to avoid all of these points and just speed up our work considerably. So here's a wish list how epidemiologic results tables should come about and can come about in 2025. To Ken Rothman's point, descriptive and inferential results can and should go hand in hand and can appear side by side in the same table. Code should produce a publication-ready table, no extra work required, and sensitivity analyses should be easy. So in the next few minutes, I'll show you some examples here using a built-in data set in R from the Mayo Clinic about precursors of multiple myeloma in relation to mortality, population-based study from Olmsted County. And later on, I'll show you data from a cohort study across 8 European countries run out of BIPS here in Bremen. So here's just a bunch of R code. For those who do not code in R, it probably just looks like code. Let's start from the back end. This is the table that it produces. And I would argue, of course, I've tried to reduce complexity here, but this is a table that you can put as it is into your paper. It has participants counts, it has event counts at person time, it has a 10-year risk, it has a 10-year risk ratio, and perhaps you want to estimate an alternative, put an another estimate, and that's a hazard ratio beyond the 10-year mark. And this is the code that produces the entire table. This is the estimate in this first column here, and this is just the label that you put on there. You could have written anything else here. We're here defining what our exposure is, what our event variable is, what our time variable is, and of course we need to tell the code somewhere that we're interested in a 10-year risk. Goes into a command called riff table. You give it the data set with a specification, put one command to say that you actually want to format a table, and that should be it. Now let's look at a few permutations, just one at a time for simplicity. So let's start with a simple version of this table, just counts and a hazard ratio, of course. There are many other estimators that we could have chosen here. Perhaps our concern is confounding, and we do want to check different ways to adjust for confounding. I think it should be, and it can be, as easy as adding 2 lines of code to this table and one column called confounders and the names of those variables. And off you go and have analyses adjusted for different sets of confounders. And guess what? There is a little bit of confounding by age going on here. Perhaps you're having a conversation with someone about the merits of null hypothesis significance testing, and maybe confidence intervals don't always need to be 95%. So for that visualization, if you don't tell this command what your confidence interval should be, well, it's going to give you 95%, but you could make it 80% or 99.5% confidence intervals. And of course, the point estimate will stay the same. But I think this is helpful to, as we think about how we interpret those results given on that width of the confidence interval that we, with our analytical choices, dial in. Perhaps we shouldn't just be adjusting for things, but we should be conducting stratified analyses. So let's add an effect modifier. Let's still give count data and, again, hazard ratios for each stratum, and off you go. Here are those results. I believe this is as easy as it should be and can be when we make our results tables. Now, of course, everything that I'm showing are all things that can be combined together and just trying to keep the code manageable here on the screen. Maybe our exposure isn't actually the presence of monoclonal gammopathy of unclear significance. Maybe we just want to look at the effect of age on mortality, or the association, if you will. And here you go. We change one line of code, and this produces your entire results table that can directly be exported into Word format, actually, or whatever format you use to submit your paper. Also, we're talking about algorithms that make results out of our data. Rounding the estimates, I think, is an algorithm that should reflect the amount of data that you have to support those estimates that you give. And Alan Wilcox, in this half a page of an editorial, can teach you more on precision and rounding than I can in an entire hour. But I hope you're on board with him and me that the North Carolina Highway Department got it a little wrong when they're giving a precision of 1.8 miles of deer on this rural highway here. And if you agree with that, then you'll also end up agreeing with giving different levels of precision, based on how high a ratio, how far a ratio measure is away from above 1. Or maybe you think that this is inconsistent and you turn it off, and that's an option too. So let's talk about making table once. And I'd like to show for that a cohort study here from BIPS in Bremen. This is the Idefix or and-I family cohort study of 16,000 children that started in 2007, 2008, and across 8 European countries with questionnaire data, questionnaires to parents, of course, because these are kids 2 to 10 years old, anthropometrics assessments, biospecimens, accelerometers. The initial focus of the study was on obesity prevention, but there's been, as with any prospective cohort study, a really broad focus on exposures that are relevant for this period of life. And of course, there's with the biospecimens, they're biomarkers and lots of focus on psychosocial health, use of digital media and so forth. So now with quite a number of years of follow-up, you can imagine this is a cohort that we're also further developing to hopefully study precursors of, for example, cancer, cardiovascular disease, and other measures that are, as we know, initiated early in life, but are often not captured during that period of life in our typical cohort studies. So how does table one of that cohort look like? Let's use the same R function. This is as easy, I think, as it should be. And if you don't code, maybe this doesn't look easy to you. But if you do code, you realize until you have this entire table, it usually takes you many more steps than just saying, these are the variable names that I want. These is what I want the columns to be. I want them to be by gender. And I want to make sure that we're rounding energy intake and birth weight to 0 decimals. Because of course, no one can measure energy intake in more than 1 calorie per day precision based on the food frequency questionnaire. And there are other measures of diet in this cohort too. So this is also the distribution of the different sites across Europe. So that's RIF table in a nutshell. It's an R package that should make producing tables on epidemiologic analyses of all sorts a lot easier, and has done so for me and for a few other people for the past 5 years. And there's a bunch of other estimators in there and interesting things. I want to highlight one more thing here, and that's regression-based estimations of risk ratios and risk differences for binary outcomes. Rothman, again, reminds us that in cohort studies, we shouldn't be reporting odds ratios, but he also admits that we frequently do because our favorite logistic regression model is what just gives odds ratios. So let's look at an example why that may be what we want. We have 2,000 people, 1,000 of them are unexposed. Among the risk for some outcome is 2%. Among the exposed, the risk is 4%, so the risk ratio is clearly 2. The odds ratio is a pretty good approximation for the risk ratio here because the outcome is pretty rare. Now let's look at the setting when our intervention increased vaccine coverage from 96% to 98%. In that setting, you don't want to go to the news media and say that your vaccine intervention increased vaccine coverage by 2-fold, because that's what the odds ratio would be. It just increased it by 1.02-fold, or perhaps you should estimate a risk difference of 2 percentage points. And your biostatistics classes may have taught you, well, that's what log binomial models are good for. Except even when you start to try to adjust for a single confounder, they don't converge. People have been trying to use Poisson models in an interesting way with a sandwich variance estimator. That often works, but it often also doesn't work, particularly in the settings when you're building your final model that you think is ready for publication. It just includes one more continuous covariate. And then there's marginal standardization, or G computation, or the G formula with time-fixed exposures. And that works whenever you can fit a logistic model, because it means you're just fitting a logistic model doing predictions under counterfactual exposures across the entire study population, and then building contrast between those. There are lots of tutorials that will exhort you to actually do this, and they're great tutorials on this. The little challenge is that they even come with R code, but the R code is typically 2 pages long. And you'll realize after having spent a lot of time on it that it only works for binary exposures, and maybe that's not the case that you're trying to work with. So there's not been, I would say, many really workable software implementations that are as easy as logistic regression. And if we want to displace logistic regression, it has to be easy in the setting. And that's a very interesting and elegant approach by Miettinen that has not gained a lot of traction, but I think that is actually, at least from an intuition perspective, very interesting. So to actually get those numbers, this is as much code as I think it should take to estimate an adjusted risk ratio. And The output looks very much the same as if you were to fit a logistic regression model. I just told you it's nice if code directly produces publication-ready results, and here's the version to estimate publication-ready results. So and we see in this population of women with breast cancer, those with stage 3 breast cancer have a 6-fold higher risk of death than those with a stage 1 breast cancer, already adjusting for hormone receptor status, at least in this data set from the 1970s that has been used for demonstrations around binary outcomes and risk differences for a long time. Maybe you're not actually interested in those substantive interpretations and you're interested in comparing the different approaches, say G computation with different ways of estimating confidence intervals, the Poisson model that happens to converge in this setting, or that interesting case duplication approach. And I would say substantively the results are very similar, but essentially we're comparing two conditional models and two marginal results against each other. That's the main difference. And for all practical purposes, I would use the G computation approach here. So now a case duplication approach that Miettinen proposed, I think is the most elegant one, at least for adjusting risk, for estimating adjusted risk ratios. Let's look at our 2,000 person population, again, now with a risk of the outcome among the unexposed of 20% and of 40% among the exposed. So again, a risk ratio of 2 with an odds ratio of 2.7. So clearly with common outcome, the odds ratio is no longer a good approximation of the risk ratio. So now we know that odds are cases over non-cases and risks are cases over non-cases plus cases in terms of counts. And when you do that, let's manipulate our odds ratio estimation as if we were estimating risks. So this is now an augmented data set where we still have our 200 unexposed cases, but we've added a copy of those cases as non-cases. So instead of 800 non-cases, we now have 1,000 non-cases. And we still have 400 exposed cases. But in addition to the 400 true exposed non-cases, we're adding those 400 and get to 1,000 exposed non-cases. And then we fit a logistic regression over this augmented data set. And what we get is supposedly an odds ratio, but it's actually estimating the risk ratio. And that is, of course, makes a lot of sense. Point estimate wise, we have augmented our data set. So we've inflated the sample size. So as you can see, this confidence interval is actually not correct. So we need to estimate cluster robust standard errors with clusters defined by the case and its doppelganger. I might argue, had this approach been called the doppelganger approach to estimating risk ratio with logistic regression instead of something like duplication approaches, and had it not been published in papers that are a little dense to read, and had it been implemented in statistical software a few years earlier than in the R package that I'm showing you here, this might be the way that we might be estimating risk ratios. But as I mentioned, for all practical purposes, this risks package that I'm showing you here, I would just use it with the default settings to use G computation, which is marginal standardization, and that will give marginal odds ratios and marginal risk ratios and risk differences. So I'm talking about modeling. In my abstract for this talk, I promised you we would actually be talking about the data behind the science. So let's do that. Now let's talk about epidemiologic cohort studies. They need to be old to be informative. And that also comes with the fact that their data infrastructure is often also decades old. In 2025, this is a screenshot from just a few days ago. This is how the baseline data of the health professionals follow-up study looked like. This is a file format that people have not seen otherwise in recent decades. This is a so-called fixed width format. It's not a database. It's just a flat file on on the disk. There are not even variable names. There are no delimiters between different variables. The string of numbers here is a bunch of different variables. I know from a specification that this one here means in the first column that this participant is married. I know that this one here means that this participant has a family history of early onset myocardial infarction. So you can imagine when you're starting out with epidemiologic analyses and with coding in 2025, and this is what you have to work with, that's a little challenging. Fortunately, in the Harvard cohorts, there are extensive data dictionaries in parentheses in an idiosyncratic format that is only readable by those SAS macros. So if you don't use SAS, then things are really hard. Fortunately, there is archived analytical code, so you can basically copy paste pages of code that has been produced by anyone prior to you doing analyses. The challenge with that is, do you really understand what it's doing and if it's doing what it's supposed to do for your analysis? And the biggest plus is there is institutional memory. Many of the investigators and the staff members have been with the cohorts for really over decades and decades. And that was a great starting point for a few PhD students, postdocs, and research assistants working together where we created an R package that makes loading these flat data files easier and more reproducible for people doing analyses and data science right now. So we're developing R functions, we're extensively reviewing them as a team, and then packaging them in an R package. You might wonder, is writing data loading R packages a great way for PhD students in epidemiology and postdocs to spend their time with? And I was not sure about the answer to that question. And the answer turned out to be yes, because our analytical scripts are no longer cluttered by pages of data loading. We can see the forest for the trees and actually start thinking about the science behind the data and the analyses that we're doing. Because we're outsourcing and different pieces of data handling, we break it down into manageable chunks. And this is a way of providing and getting feedback and doing this code review that I was referring to earlier on that overview of the research community approach, now in manageable chunks that people can actually give feedback on. We have learned an embarrassing amount about the data. I'll leave it there. And the most fun thing about it is we're not alone. This has created a community of people working together on a task that no one would want to deal with by themselves. I'd like to direct you to a website that's called code.harvard.edu/HSPH API, and everyone with a Harvard key account who's working on epidemiology is welcome here. You see that it started off with the prostate cancer epidemiology team, but even at Harvard, there are not 105 people working on prostate cancer and not working on 112 projects a few days ago here. This has really grown tremendously to include a lot of people who use this code sharing and versioning platform to discuss analytical decisions, to give feedback to each other, and to document analytical decisions and really talk to each other. Now, why do we use Git and GitHub, and why does Harvard, at least so far, actually fund this? Because this is industry standard. Everybody who works with code essentially uses Git, and GitHub is one of the products that puts a nice website on top of it. And one of the big draws here is a strong social media component to collaboration around epidemiologic analyses. You see, even for a small change, it's easy to add the documentation, to link it to other discussions here. You see these blue things here are clickable. And there is a built-in mechanism to receive feedback from others and to do all of this work asynchronously without having to sit at the same time in front of the same script. And it makes code and results accessible for those, including people who do not code or who have not coded in many years. Or perhaps you can look at help pages of, say, this one package that I was mentioning. If you're wondering how many current smokers there are in the health professionals follow-up study in the 2020 cycle, the answer is 259. So apparently smoking is not very popular any longer among health professionals, or not very compatible with living beyond age 80. So I've talked a lot about code.harvard.edu, and I mentioned the word GitHub. So are we talking about public code on github.com or shared code at code.harvard.edu? So let's first start with sharing code publicly when it's final. And that's a great thing, because it allows for the reuse of the actual method of not what people think it might be based on reading our short description and methods section. It allows for reuse of code by those who cannot easily replicate it. And that's 99% of us, because replicating and writing good code to implement methods is just freaking hard. And it's also very useful for teaching purposes. For example, I did this paper on the form of differential measurement error a few years ago. For example, this is a little plasmid simulation study built in there. And I often send people to this GitHub page on the public internet, because there's not only the figures again, but the exact code that produced these results. So sharing code publicly when something is final in terms of analysis is great. I would argue sharing code internally before it's final is even more important. And that's because not putting something on the internet, but in a safe space, that's important for trainees to grow. And it's important for everyone, because you can ask questions and people can share their insights. You can create resources that may not be publicly shareable, or it's not desirable to do that. And it's great for things that are so idiosyncratic for your one study that there may not even be a need to put them anywhere on the internet. Now, before I end, I'd like to talk a little bit about how to train people in all of this, how to train people in epidemiologic data science. And I don't think that serendipity is a strategy. So my serendipitous path from starting off with an interest in math and informatics, but then studying medicine and going back to epidemiology because I was missing those numbers in medicine, that's not exactly a strategy. And I was just very lucky to meet Travis Gerke, who graduated from the doctoral program in 2014. I essentially learned everything about data science and epidemiology from him, or from trainings that he talked about. He's now the founder of a company that uses large language models to implement DAG-driven causal workflows. So what is a path forward to train people? I do believe that epidemiology students do need basic training in algorithms, not just in data analysis. And this is something that I had learned well before I went into medicine, for example, and well before I went into epidemiology. But maybe it can be taught even more formally. Collaboration skills around data structures, and around code are just key qualifications on the job market for whatever job people may be taking that has a relation to epidemiology today. I'd love to make a plug for using real software in class that students will also use in real life. When I trained, a lot of the training involved handheld calculators or Excel sheets in which you could do standardization, for example, and really I appreciate how that works. Yet, of course, you would never use that in an actual study. And if we teach one tool, one way of doing things, maybe not even the algorithm behind it, and then expose people to real world problems, we shouldn't be surprised that they go to Dr. Google and Dr. Google will tell them to use logistic regression to get p-values and not the fancier things that we would love for people to use. And lastly, if we really want to teach transferable skills and want to make a dent into making research reproducible beyond following up on what funders and journalists are requiring from us, then we should really think about using globally accessible, non-commercial software, because that is just a prerequisite for that people can reuse things that they learned during their training, and that people at other places can access the code that we share with them. So I've been trying to put all of these things into action, and I can only report back on 1 month of experience, because that's how long this course in advanced epidemiologic and statistical methods has been running here at the University of Bremen. I just sort of used a data science first approach. The entire course, say, lives on GitHub. Everybody is in a GitHub organization. People make their changes to their class materials through commits. They submit their homeworks with pull requests and so forth and so forth. And well before we even think about how variance estimators look like, but we do start with stratified analyses with our code. So with that, I would love to wrap up, and I'm curious about your questions. So to summarize about epidemiologic data science, I'd love to make a plug that we should start with structuring our epidemiologic data science before we jump in, or maybe at least at the same time as we jump to artificial intelligence-based tools. I do think, even if it is effort, that we can teach algorithms and collaboration with open source software somewhere along the curriculum. And from the experience of the past 4 years that I've shown you from with code.harvard.edu/hsphAPI, I think we've made a strong case that building a research community around analytical sessions and programming code helps everyone, even if you don't code yourself. With that, I'd love to send you to a place where you can learn more from people who actually know something about these things. Unlike me, this is a session at the SDR meeting in Boston in about a month from now, where Travis Durkee, Emily Reeder, and Malcolm Barrett will be speaking about how to implement more of these fancy things that I touted here in real life. With that, I'd love to give a shout out to Travis Durkee, but also particularly to Bailey Vasilkiv and Hannah Gard, who are data analysts / research assistants in the Department of Epi, and who are behind that success of having over 100 people on the GitHub so far, because that does require responding to a lot of emails saying, thank you for the great question. Can you ask the question again on GitHub? I promise you will have insights from 3 additional people besides my response that I could put in an email. And in the long term, that has paid off already. Thank you for your attention. My email is here because I would love to hear from you, both about data science and of course about how we can be stronger together across the Atlantic. Thank you so much.
Dr. Stopczak, Konrad, thank you very, very much. This was very enjoyable and a very good illustration, actually, of transatlantic work. I have first now to say, and not to forget, that from now on, we will continue to record this, so Q&A will be recorded as well. With that said, anyone who would like to ask a question or make a comment, please go ahead. I have a question in, no, I have them here. I go to later to the chat, but I go to Anmol Pardeshi. Anmol, please go ahead.
Hi, thank you so much, Conrad, for the amazing talk. I am currently a PhD student in Epi at USC, and I congratulate specifically one of the slides in the later part, which highlighted a few things to look forward to. And I can concur that epidemiology students need to learn some data science algorithms, because if people are going to industry, and these industry-based jobs will essentially have those initial coding rounds, which are going to be very beneficial. And the second part, which I wanted to add on that, was um, people who are doing genetic epidemiology or epigenetic epidemiology like myself. It's good to know those algorithms, because we would have to implement like large scale GWAS or EWAS studies, and therefore knowing how to do parallel processing or using the high performance cluster, something like that. So I am very much in sync with that. So those are the comments that I have. The only thing which I would also like to see being added is the importance of exploratory data analysis, in light to a very recent event that I had, where one of my colleagues from the wet lab, they sent me some data, and there was like a huge discrepancy. When they ran t-tests one way, there was a non-significant, utterly non-significant p-value. Then they changed it the other way around, and they came up with a significant p-value. But the problem was that the data was extremely skewed. So you tip it one way or the other, the ratio will change, and it will lead to significant, non-significant results, kind of tending towards p-hacking concept. But so what I'm saying is absolutely in sync with what you said, just that maybe the exploratory data analysis can be added to this. But thank you so much.
Thank you.
It's really enjoyable.
Thank you for your comment. Of course, I agree on exploratory data analysis, and from an epidemiologist perspective, I would frame that as we need to start with a description and with actually looking at our data, and need to properly describe it, and that definitely needs to be part. And what data science does is it makes us comfortable actually doing those things, rather than trying to hide everything behind one hazard ratio.
Let's go to Dr. Puyat Vincente. Please go ahead.
Thank you so much, Dr. Conrad Stopsek, for the talk. I actually used both the packages you mentioned, Riftable and Risk here. And I had a question on one of the suggestions you had first was a lot of epidemiologic training focuses a lot on the analysis and the models in this case, but I find that a lot of replicability comes from not understanding how different epidemiologists transform the data for their analysis. So in terms of moving forward, should future epidemiologic training postgraduate programs incorporate explicit lessons on how epidemiologists should standardize processes to transform data from raw data, as well as be exposed to data sets that have a lot of problems, such as missingness, incoherent data, misclassification, and whatnot?
Yes, thank you for it. That's a great comment. Of course, there's so much data science and epidemiology that I couldn't cover. And yes, the most important part to learn in terms of data science and epidemiology is how to align epidemiological thinking with that data cleaning step that we like to sweep under the rug, but that effectively takes 80 or 90% of our time, and has probably, compared to its visibility in our results tables, an outsized influence on the results that we get. So there is, I think, as you allude to, there is both training that in terms of algorithms, in terms of orders in which things need to be and how they need to be done, that's critical there. And the other part is that in at least internal code sharing, you probably don't want to be doing all of this publicly on the internet, but you do want to do it in your team. You do want to be able to ask for help. And that's what we've seen, this code.harvard.edu forum on a GitHub Enterprise to be particularly helpful for. It's not the modeling part, it's the data, it's the pre-processing part that these tools are particularly helpful. And that HPFS package that I showed, that's all about data loading. It's not about any modeling at all.
Thank you so much.
Thank you very much. Yes, in the chat we see that code.harvard.edu, you have to be added to the repositories, isn't it? So, or to see the content,
Yes.
you have to be part of it. Yeah.
Yes, I do see. I'll just quickly get the link here updated. So this is the link, and then Bailey Vasilka, if I see her on the call, is the person that will take your, and
There
there
she
she is
is.
with a video. She will take your username once you log in once. It'll record your username, and that username is needed to be added to the organization.
Thank you, Bailey. Huh?
Yeah, I'll put my
Yeah.
email in the chat. So if you're interested in being added, you can just email me your username and I can add you.
Right. Thanks.
Thank you.
Victor Tsao, would you you have another question in the chat? Would you like to ask that, or shall I do it for you?
Yeah, I can ask. Thank you so
Please.
much. I'm
Yep.
an incoming NPH in epidemiology student, and I work in the industry. I work in a virtual primary care practice. So a lot of the comment about using coding languages that the general public can understand. So you mentioned R. Do you recommend Python, or R is the #1 choice in the epidemiology/public health space in the industry?
Yeah, that's a great question. I don't know that there is one right answer that fits for everyone. It depends on what you do. I would definitely say the more advanced the statistics are that you do, and the more data science there is, and that is aligned with epidemiological thinking, the better off you're probably with R. The more you're towards machine learning slash neural network slash AI model fitting, the better you are off with Python. At the end of the day, the training that's important is around algorithms, and the other part is that code needs to be accessible and actually runnable by people. So either R or Python are free, open specifications, no licenses required. So that part is way more important than which of those you do choose. But at the end of the day, yes, statistics professors write R packages. And I do think epidemiology professors should be writing R packages too.
Awesome.
Well,
Thank you so much.
Python.
Increasingly, huh? Yeah. Can I ask a question, Conrad? I thank you, by the way, very much for making the link with teaching, because that is really quite important. So I wanted to ask, what is the best place in a general epidemiologic curriculum of this, and what is the volume? I saw your course that you mentioned in the first week, EpiStat 2, is a course of 270 hours. I guess that is not all this. This is an element of it. Perhaps you can comment a bit on this.
Yeah, I don't know that I have the final answer to this, and I think this is very much something that one should test empirically what really works for people. For my intuition, I would say putting what I'm doing in that course, and by the way, the 270 hours do include self-studies and homeworks and so forth.
Yeah.
But it's I think putting that first so that it becomes second nature to just be putting these say things on GitHub to become, as you're saving a file, you're also committing it, that this collaboration that you're starting off with that early on, even if you don't know yet how to fit fancy models. I would probably err on the side of introducing those things early, but then to reuse them in bits and pieces along the curriculum so that things come together and you're not being taught 3 different approaches to algorithms, programming languages as you take 5 different epidemiology courses.
Thank you. I don't want to put anyone in the audience on the spot, but Murray Mittelman, if you have a comment on this last particular question, either you can do it now or later on bring it to us. Well, Murray is there, so perhaps you have a comment on this one. What do you think?
No, I don't have anything specific. I think this is really terrific and important that we start to incorporate these approaches into teaching, and that's true, I think, in the in some of the core and also more advanced epi training courses, as well as the biostat. And and I think that in terms of what to use, the prior question, and I completely agree with Conrad. I mean, I think it's very individual, and there is no single right answer. And I know a lot of our courses at Harvard use other software packages besides, right? A lot of people like to use Stata or SAS or other things. And I think, that's fine. Being multilingual is a good thing in life and also in research.
Mhm.
Danke sehr. I was saying that. Okay. Well, we know we have a hard stop, Conrad, and so I would like to start by thanking you by reading something from the chat. Mara Rubia from Porto Alegre in Brazil writes, Mara, thank you very, very much. She said, thank you for this very informative webinar. And I cannot agree more with Mara, and I thank you, Conrad, very, very much for your seminar, for your webinar, and look forward to further collaboration transatlantically.